Good morning, everybody, and welcome to the part 3 of the NHERI GSC and SimCenter Research Tools Workshop Series. My name is Rakesh Salanke, and I'll be moderating this workshop. Today's workshop is on developing and benchmarking fragility and consequence functions, presented by Dr. Adam Zarnozay. This workshop series aims to introduce various tools and resources made available through NHERI SimCenter and Design Safe Cyber Infrastructure for natural hazards research. Graduate students and researchers can learn and use these tools and resources for free. This workshop series was conceived and organized by the NHERI Graduate Student Council in coordination with the NHERI SimCenter. For those of you who are new, NHERI Graduate Student Council was established more than a year ago with a vision to build a diverse community of graduate students focusing on natural hazards research, and to connect with experts and mentors in the natural hazards community, to create opportunities to attend a variety of natural hazards research workshops, such as this very workshop series and others for career development, to encourage the important conversations of diversity, equity, and inclusion within the natural hazards research community and elsewhere, to learn about the multifaceted impacts of natural hazards and the research practices, and finally, to gain leadership, service, and funding opportunities. If you are new to NHERI GSC and not yet a member, but would like to get involved and benefit from the various events and activities, we welcome you to join the NHERI GSC by scanning the QR code on this page or by using the link below the QR code. It has been a fantastic experience for me to be a part of the NHERI Graduate Student Council, interacting and working with a diverse group of interdisciplinary graduate students, and having opportunities to hear from experts such as today's speaker, which have offered very rewarding experiences. I have no doubts that these experiences will have a lasting impact on our careers, whether in academia or in the industry. I would like to now introduce today's accomplished speaker and presenter, Dr. Adam Zarnozay. Dr. Adam Zarnozay is a research engineer at the John A. Bloom Earthquake Engineering Center at the Stanford University, where his work focuses on disaster simulations that support multi-hazard risk assessment and management at a regional scale. As Associate Director for Research Outreach at the NHERI SimCenter, he connects to researchers and practitioners to understand the state of the art and foster collaboration in the natural hazards engineering community. Adam obtained his PhD in civil engineering at the Budapest University of Technology and Economics, and also completed 2 years of graduate studies at the University of Tokyo. He has experience working at scales ranging from an individual structural member in a building to cities with hundreds of thousands of assets. His research interests include probabilistic natural hazard assessment, model development and calibration for structural response estimation and performance assessment, uncertainty quantification in large-scale regional simulations, and using quantitative disaster simulations to support risk management and mitigation. I should also note that Dr. Adam Zarnozay has been a friend of NHERI graduate student community since our organization's beginning and has delivered several presentations in the past and has also been of great help in putting together this workshop series. So thank you, Dr. Adam Zarnozay, for that. Before we proceed, I would like to inform the audience members that we will have a Q&A session at the end of the workshop. So I request that you hold all your questions till the very end. So with that, without further ado, I would like to hand it over to Dr. Adam Zarnozay to begin the workshop. Let's stop sharing my screen.
Thank you, Rakesh. And thank you all for having me. It's always a pleasure to be here and present to this group. Let me figure out sharing. Okay. So you should see the slide. Please confirm that it works properly.
Yes.
Presenter. Yeah. Excellent.
Works.
Okay. All right. So we will have about 40 minutes or 45 minutes of a presentation. Maybe it will be 50, it really depends. And then I'm hoping that you will have some questions and you will have some prompts that are not only interesting for the sake of this workshop, but also helps us as developers of these tools to understand where to expand and what features to add that you might be interested in and are not available. I can also point you to additional resources if you have questions about certain things that I do not mention in this presentation, but you feel that you would be really interested in. So please have some questions. If something comes up, save it for the very end, but don't forget to ask it. If you cannot ask it because time doesn't allow, please send me an email or send us an email, and I'm more than happy to get back to you and discuss the problems that you are interested in. So talking about today's workshop, we are looking at developing and benchmarking these fragility and consequence functions, or more specifically, how the SimCenter tools can help you developing and benchmarking new fragility and consequence functions. We will start with a short introduction to the SimCenter. I know I see many familiar names and faces, so probably you already know what the SimCenter is, but I always expect some new people, and for their sake, I want to give a really brief introduction, and then we will look at today's topic. So first of all, I want to acknowledge that the SimCenter is a large team. You can see many names on this slide. These are all people affiliated with the SimCenter. Everybody contributes to those things that I present. So please remember that this is not just my work and my results. I am only the messenger here. The SimCenter is part of the NHERI infrastructure. I'm sure as members of the Graduate Student Council, you are aware of what NHERI is. You can see all the sites here. SimCenter is headquartered at UC Berkeley, and it is somewhat special among the other centers that are part of NHERI because we are focusing on virtual experiments, computational simulation, while many of the other centers are interested in experimental work. What our objective is to accelerate this innovation in the computational simulation domain by providing access to a simulation platform and training people to use that platform, which allows them to use different kinds of models and experiment with different kinds of approaches to solve problems in natural hazards engineering. This is a really broad mandate. And the way we try to tackle this is by taking the performance-based engineering framework that was originally developed at the Peer Center at Berkeley, and then increasing its scope, expanding its scope beyond a single building and beyond just seismic hazards. So if you know what this performance-based engineering framework is, you know that it is decoupling the parts of the calculation of a performance assessment calculation into a hazard analysis, a structural analysis, and then a damage and the loss analysis. Using this same idea, we decouple simulations in general into different pieces, and we use those pieces to assemble different workflows, as we call them. So starting from this peer idea, we arrive at these puzzle pieces that we call the SimCenter application framework, where each puzzle piece represents a method or a tool or a model that you can use. And we make sure that the connections between these puzzle pieces are standardized so that you can plug in another piece if you have your own model or if you have your own idea. And I would say that this is true at a high level at the SimCenter application framework. And if you go into each puzzle piece, we try to follow the same idea. So within the puzzle pieces, the different parts are interchangeable. And this is very relevant to today's presentation because the fragility functions and the consequence functions that you use for performance assessment come in a similar fashion. There's a standard interface, as I will show you, and you are able to replace the default or the built-in functions with ones that you have developed in a very easy manner. So using these puzzle pieces and the idea of flexible workflows, just to illustrate what you can do with the big framework, when you are not focusing only on performance assessment, you can do an earthquake risk study, for example, perform that, and you can see that for the hazard, exposure, response, and damage and loss steps, you have multiple options available. This is not just a sketch, this is actually what's already available in our framework. So you can choose between different levels of fidelity and different modeling approaches for each step and decide which one is fitting the problem or the study that you are actually involved in, and which one you can provide sufficient data to expect robust results. Now, zeroing in on what our topic today is, let's look at one puzzle piece, the damage and loss one, the performance assessment one, among all of these 6 different ones that are part of our application framework. Here, we do something special. We are not pulling in different tools from the community because there was no single tool that would do the job. The SimCenter is developing a new performance assessment engine, a framework, and its implementation in Python. We call this Pelican. Pelican is an acronym. You can see the full name here. And the idea here is that we want to have a unified approach to performance assessment that is not specific to a particular kind of resolution. Think about FEMA P58, if you know what that is. It's a high resolution framework. There is HAZUS, which is a more lower resolution, efficient methodology, but even within HAZUS, you have different approaches under earthquake hazards and wind hazards and flood hazards. So what we try to do with Pelican is to bring all of these together into a single framework so that people working on in different areas would find it very easy to communicate and to share their insights and know-how on how to model certain kinds of building performance questions. We already have quite a few things available in Pelican. So it supports earthquake, wind, and water hazard-related analysis with fragility data and consequence data for hazard-style assessments, so efficient assessments. And then for high-resolution cases, we have the FEMA P58 library built in for earthquakes. And we are looking for researchers like you to fill in these missing parts by doing new research. There is no methodology currently available for high-resolution wind performance assessment. There are some researchers working on pieces, and we are reaching out to them and bringing in their fragility curves, bringing in their consequence functions. And I encourage you, if you are working on those areas, to share your results with us after publication. It's okay, you don't have to share it before it's safe. But once it's published, if you share it with us, we will share your results with the entire community so that everybody can use the fragilities and the consequence functions that you developed. That's how we can get from this level all the way up here, where you are able to do subassembly level loss assessment under wind hazards or flood hazards. And we are also interested in expanding beyond buildings to pipelines and other types of assets of the built-in infrastructure. So there's a lot of room for improvement. And what Pelican provides is a framework that can accept all of those contributions without you having to work too much in formatting the data or learning a completely new type of storage for each type of hazard. Now, we do have most of our applications developed in C++ or Python. And if you want to directly interface with our engines, it's done in the command line. But to make it easier for students and for those who are new to this framework to get started, we also have desktop applications. So we take our backend framework and put a nice front end to it, in front of it, which has a user interface, buttons and visualizations, and it makes it easy to set up an analysis, run, and then get the results back and view them. This is an example here of our regional simulation application, but we have similar ones for many different purposes, going from using only a few parts of the framework to focus on calibration exercises. In a hierarchical manner, we go to more and more complex applications and reach the R2D tool, which is our regional simulation tool. Today's workshop focuses on 2 tools here at the top of the hierarchy that involve this damage and loss module. The first one is PBE. I will work with PBE today, and the examples are developed in PBE. This is for individual structures, so for one building or one type of asset. It could be a bridge, or it could be any kind of other asset, but it's a single one. And then R2D is scaling up PBE by having a portfolio of assets, so it is capable of regional scale simulations. So if you look at PBE, you will see this application later today. What we can do here is set up an assessment using either a HAZUS style method or a FEMA P58 style method, or your own method if you have your own methodology to do performance assessment. So you're not only interested in changing the fragility curves or changing the consequence functions, but you are actually developing a new way to say, consider cascading damages in a wind and storm surge scenario. You can do it there. It would be a little more involved than what we are doing today. The basic built-in functionality is HAZUS and FEMA P58, and you can bring in your own response estimation results. So if you are working with an earthquake kind of problem, you can either do the simulation within PBE with OpenSeas, or if you use some other tools, say you use ETABS or Perform 3D or Abacus or ANSYS to get some response that describes the building's behavior, you can save that in a file and load it in, and then do only the loss assessment, damage and loss assessment in PBE. We have a number of webinars already on PBE online, so I'm not going to describe everything about PBE. If you don't know much about the software, then focus today, I suggest focus on the fragility and consequence data. That is the topic of today's workshop. And then in the end, I will show you some resources that you can use to get up to speed about the other parts of the application. And of course, there are other webinars coming in the future that will also show you more information. And there's a documentation that you can also use to learn more. Now, PBE was for a single structure, as I mentioned. There is R2D, which is a regional simulation tool. So you take what you did with one structure, and now you can do it with many. The many can be as many as millions of buildings. We are providing you a connection with high performance computing resources in Texas. That's the DesignSafe project. You probably have seen at least one presentation about them if you are regularly coming to these workshop series. So you can use their resources to run these expensive simulations. And you see that we already support different types of hazards, and not only buildings, but also lifeline kind of analysis. Traffic networks are also coming in the, or transportation networks are coming in the near future. So this, these types of analysis also need fragility and consequence functions, and the same kind of data and the same kind of approach to extend what's already there applies to R2D and PBE alike. That's why I wanted to point out the availability of these tools. Now, about today's talk, what we will focus on, if you look at what PBE does, it includes structural analysis, damage analysis, and loss analysis. And although we usually say that you only need to provide a location for the building and some design information, another part of the calculation that is important is fragility and consequence data. In most cases, people don't worry about this too much because they say, I'm going to use FEMA P58, and then they expect that FEMA P58 data is already built in PBE, so you don't have to worry about where it comes from, how it looks like, how to extend it. Same thing for a HAZUS style analysis. But I'm hoping that some of you are interested in developing new fragility functions. Maybe you are working with an experimental facility, and based on experimental results, you will improve the fragility functions that are already available in the literature. Or maybe you are working on a new kind of structural member, and you need fragility functions for that member to be able to characterize the performance of a design that is made with such members, right? So there are a lot of options. Or maybe you have consequence data in FEMA P58, but those data sets were developed for California or perhaps for the US, but you are not in the US. So you want to replace those consequences with specific ones for your location, Europe or Asia or Africa, right? It's very different how much it costs to repair a certain kind of member. So what today you will learn is how to do that, how to take what's already available in PBE or Pelican and extend, edit, or replace it with other functions and parameters that are specific to your needs and research. We will look at what data sets are bundled with our tools. We will look at how to change them. And then we will also see two examples where I'm benchmarking different models within the next 30 minutes, let's say. So when it comes to fragility data, if you open the PBE application, and I will demo this, but I don't want to always switch between the presentation and the demo, because I thought that that will just be too time consuming. And this way you have it preserved here, so you see what I'm clicking on and where the important pieces are. So if you open the PBE application and you go to the damage and loss panel, which we will spend most of our time with, then you see there are 4 steps here. You need to define some kind of an asset with components in it. So what kind of components make up your building, for example. Then you need to define the demands. Think about accelerations, drifts, wind speed, such things. Then you work with a damage model and a loss model. So first, when you think about fragility data, it is defined in the asset part because it is defined when you tell what kind of components are part of your building. This is true for a FEMA P58 analysis, which is high resolution. You would go down to the member level. You would say, I have columns, I have partition walls, I have windows, things like that. But if you use a hazard style analysis, it's the same conceptual idea. You just don't go down to those individual members, but you say, I have structural components, I have non-structural components. So those are 2 types of things that you add to your building. And it's the same for a hurricane type of study, and for basically everything you do here would be based on these components. Now, you can see that among the databases, there's a drop-down menu, and we have FEMA P58 and hazardous earthquake available in PBE. We also have a hurricane model available as a data set, but it's not yet featured in PBE because PBE so far is focusing on earthquakes. The hurricane data is available in R2D for regional assessments. And I will also talk about this user-defined one later. That's where your ideas and your new fragilities come into play. So if you load a particular data set, let me go one step back. If you load, let's say, FEMA P58 here, you will see what components are available. I think it's better this way. You will see what kind of components are available in that data set in this menu. There's 756 components in FEMA P58. So if I open this dropdown, you will see only a part of them. But you can scroll through and you can select any of those for your own analysis. And then once you selected them, you can assign them to your building and get some information about each. So it's pretty convenient within the PBE tool. You can see what components are available and what the component ID really means, what kind of component it describes, right? And then below here, you assign the component to particular locations in the building. I am not going to describe that in detail in the interest of time. We have it in the documentation, and we have other webinars that talk about those things. So this part is used to assign those components to the building. Now, the important thing is that these are built-in data sets that you might want to change. You might say that I want to take a look at this data and only change one parameter of one component because I don't like it. I looked at the FEMA P58 background documentation, and I know that that particular research is outdated. But for everything else, I like what's there. So you don't have to come up with the entire data set again. You just select one and say export DB, and you will get the data file exported to a location of your choice. You can open it. You will see it's a CSV file, so it's basically a table, and you can edit the parts that you want to edit and move on, load it back, and then use it in your analysis. This is what we will look at in the demo. Now, if you don't want to use PBE and you are just interested in the data, you can get it directly from GitHub. Here is the link. It's basically in our NHERI SimCenter user under the Pelican repo, and you can see under resources, there are all of the different consequence and fragility data available, and it's always updated to the latest version. So even if PBE is behind the latest version of Pelican, you can go here and check out the data sets that are available. Now, how do these data sets actually look like? So I took these fragility ones here, and enlarge them, you can see that there are CSV files and JSON files. The JSON files are optional. They provide metadata. They provide additional information and description about the components. These are not necessary for the calculation, but they are, in my opinion, necessary for sharing your results with other researchers so that they can understand what are the application limits of that particular component and the corresponding functions. The CSV is absolutely necessary. That's where the parameters of the functions are stored. Let's see how it looks like. For the CSV file, I opened it here. This is a FEMA P58 dataset. You might not be able to read these lines, but that's okay. I just want to show you the structure of the file. There is a header that uses multi-level indexing. So we have groups of columns in the header, and the groups are separated by a dash. So you can see this is demand type, demand unit, demand offset, and demand directional. That means all of them are demand related. And then the next group is LS1 and different parameters, LS2, LS3. So the LSs are limit states. We use limit states and then damage states in PBE. Limit states are described by the fragility functions. And after a limit state is exceeded, you experience some damage that might be described by a single damage state or multiple damage states. It is possible, and it happens quite often in FEMA P58, that you exceed a limit state, and there are two different damage states that can happen. Okay, so two different forms of damage. For example, in the component that we will look at today, there's a reinforced concrete column and beam, and the damage could expose only the transverse reinforcement or the longitudinal reinforcement as well. If the longitudinal reinforcement is exposed, you have a different repair process to go through, so the consequences will be different. But the limit state is the same. So at a certain drift, you experience the damage, but the form of damage can be two different types. That's described by damage states. This is different from the typical FEMA P58 language or vocabulary that is used there. Okay, so we have LS going from 1 to n. You can have as many limit states as you want. There is no limit there. Usually, it's not more than 4 or 5 per component. And then for each limit state, we have parameters that I will look at in the next slide. The demand part describes what kind of demand causes this damage. This is typically in an earthquake setting, you think about either some kind of spectral acceleration or PGA, or response quantities such as peak interstory drift or peak floor acceleration. When you have an incomplete column set to 1, that means you are still working on that component. It should not be used for the calculations. This allows you to have prototypes in your database, and you don't have to worry about accidentally using them for a calculation. They will be skipped if you happen to choose them for any building. And then an important part is that each row of this database or of this table corresponds to a single component. So if you have a FEMA P58 type of study, then each row is a type of member or a type of non-structural component. Think about beams, braces, partition walls, these kinds of things. And in one row, you define all of the limit states and all of the fragility functions for that component. If you think about a HAZES style of study, then one row would be a structural component description. The other row could be a non-structural component description. Okay. Now, let's take a look at the demand parameters. For the demand, you need to know the type of demand, the unit of that demand, and then there are two more parameters that are more advanced that we won't go into those details, but you can see the documentations. Now, your first question might be, what kind of demand types are even available? So I have this slide for you. These are the demands that we support right now. You can see that there are different types of hazards included here. Drifts are typically for earthquakes, but for example, wind intensity or inundation are not earthquake related. So all of these are already supported. And if you need to put in exactly this text into the fragility database so that we recognize that you are talking about that particular kind of demand. And then we would expect that you will supply those demands. You will provide the information of what kind of drifts or floor accelerations are in the building, so that we can calculate the damage states later. Okay, so inside the fragility database, here is demand type. This is where you put your select type from this list. And this list can grow very easily. It is part of a Python script, and I can just add a line, and then we have a new demand type. So if your demand is not here and you want to extend this list, just send us an email, and we can add a new line for the next release. Okay. Now, besides the demand, I mentioned the limit state parameters. This is where you can see what are the possibilities for you. What kind of fragility functions can you even think about? When we say fragility functions, most people immediately think about log normal distributions and the typical log normal fragilities. But the most basic fragility function would be a deterministic one, where you provide no family, so there is no randomness, there is no uncertainty, but you only provide a single value, like a capacity of a component, and it will fail exactly at that value all the time. So you have the demand here, and that a particular value that you provide in this table, you enter from limit state 0 to limit state 1, if the demand exceeds that, right? If the demand is even bigger, at one point you enter from limit state 1 to limit state 2. It's deterministic, there's no uncertainty. This is the basic. This is often used still in wind engineering, for example, when you have subassemblies and you have some results on their capacity. Now, if you go beyond that, you have normal or log normal distribution options. So that means you would get something like this. This is more familiar, I assume, where you provide the median capacity, that's the first parameter. And the second parameter is either a coefficient of variation or a log standard deviation, depending on the choice of normal or log normal distributions. So this allows you to have such fragility curves defined with a few entries, basically a family and 2 parameters in this table. The damage state weights allows you to have more than 1 damage state per limit states. I mentioned this just a few minutes ago. So you have a limit state. If it can lead to multiple options in terms of damage, you need to provide the probability of each occurring, right? It might be 60% of the time you have damage state 1, 40% of the time you have damage state 2. You can see an example here. This is from FEMA P58. The first limit state, 95% of the time leads to 1 damage state and 5% of the time leads to another one. This is what it does. For a simple approach, you just skip this, and you always have 1 limit state leading to 1 damage state. So this data schema, I explained it using FEMA P58, but it's the same even if you use other methodologies. So I switched to HASS. Now I'm showing the HASS data set. You can see that the IDs changed to structural, wooden one, and high code, for example, in the first row. And we are still having the exact same structure. And that is advantageous because you can mix and match things. You don't need to worry about what methodology or fragility will be used in. You just need to worry about describing those fragility functions, and then people can decide what they use for a particular study and assemble a table for themselves. So what about the JSON files? You have these CSVs with the parameters, and then the JSON provides you information, background for the components. You can open these JSON files in Firefox, so you don't need any special tool to see them like this. And you will see that for each component ID, we provide information about the component, and then we provide a description of the damage and the repair action that corresponds to it. This is not set in stone. You can add more features or more attributes to this JSON if you want to provide more information about your fragilities, and you can expand it as much as you like. I suggest not overwriting these existing attribute labels, because we use them in some tools, but if you add new ones, it's not going to hurt anyone. So we are expecting the community to explore what features or what descriptions are useful to have for fragilities, and then we will arrive at a mature metadata format eventually. We don't want to say that we have the experience to tell you how to do this. We would rather work with you all and come up with something that is useful for everyone. Now, how do you extend all of these? So what you can do is open a CSV file and simply change the parameters there. Once you understand what they mean, it's pretty simple. You can also add new components by just adding a new row in the CSV file. You give it a name. You are completely free to choose any kind of ID, and then decide how many limit states it has and what the parameters for each limit state are. You can also edit the metadata in the JSON file. Just open the file and change the text. Or you can create a brand new file. You don't need to necessarily work from an existing one. As long as you follow the same header structure that is in our standard format, it will work. And then once you have that file ready, you can use the user-defined option here to load the file into PBE. And from that point on, you can work with that file. You will see the components that you defined in that file, and you will be able to run the analysis immediately with those components. It's that simple. So we looked at fragilities. Now let's take a quick look at consequences. It is somewhat faster because you already kind of get the idea, and that is the same logic. So consequences are loaded under losses. They are separate from fragilities. We believe that decoupling these things helps with thinking about the problems. In some methods, they are merged. For example, in FEMA P58, a component has both of those things described together. We believe that there is an advantage in talking about these things separately. So even if you choose FEMA P58 here, you only get the FEMA P58 consequence data under the losses, and you have the fragility data under the asset. We have the same kind of things available here. So we have FEMA P58, the earthquake model from HAZUS, and the hurricane model from HAZUS currently available. We are working on others, and we are also collecting individual components from the literature, which are not these big developments, but little things, but together, all of them can help a lot, because even FEMA P58 is now, well, the latest release is 4 years old. So there's new things in the literature that would be good to share with the community. Now, from damage to losses, when you do the calculation, you need to tell PBE which damage is described by which damages consequences are described by which loss component. So you don't need to have the same IDs in general, but in order to do this automatically, it's better to use the same ID, because then PBE recognizes that these are the same things. Imagine another example. Imagine that you want to have a replacement consequence. That replacement consequence could be connected to different kinds of damages. Collapse could lead to replacement. Irreparable damage could lead to replacement, right? So there are more complicated mappings possible. But for a simple case, you want component A, and the damage of component A is described then by consequence A. So A linked to A, B linked to B. That makes it much easier. Then you can use the automatic mapping. If you want to do more fancy things, just choose a different mapping here, and it will work. Now, again, this database can be exported like the damage one, and you will see the CSV files, or you can go to GitHub and you can see the building repair CSV files there in the same folder that I showed for the fragilities. Now, if you look at these, it's the same idea. You have CSV and JSON files. The CSV contains the parameters, and the JSON contains the metadata. When you open the CSV file, again, it's the same hierarchical multi-level indexing structure. We have a little fewer groups here. We have ID and incomplete, like we used to have in the fragilities. And then these two columns describe the units for the quantity that influences the magnitude of the consequence in the median consequence. And then you need to provide a unit for the output. So maybe you are talking about repair cost, but that repair cost could be in dollars, it could be in pesos, right? It could be in euros, it could be in a 2011 based dollar value or a 2018 based dollar value. So you need to describe what it is. Here you see again a FEMA P58 example. where the consequences for cost are in dollars based on its 2011 value. And then each of these bigger groups here correspond to a particular damage state. So for one damage state, you provide the consequences, then you provide the consequences for the other damage state, and so on, as many damage states as your component has. If you look at what kind of parameters we need for the damage states specific consequences, you need to understand the different kinds of consequence functions that we can support here. We can support either deterministic or probabilistic consequences. If you have a deterministic consequence, much like we talked about deterministic capacities for fragility functions, you just don't say anything about the family of distribution. You keep it empty. And that means if your component is in a particular damage state, the consequence will be X, always. There's no wiggling around the value of X. If you have some distribution described, like a normal or a log normal, and we can expand this with other distributions if you need such things, then you would look at something like this. So depending on the damage state, you have losses that have a distribution around the median value. To describe this distribution, you use the same idea that we described in the fragility functions. You provide a median, and then you provide either a coefficient of variation or a log standard deviation. Now, the median consequence could be either constant or multilinear, and I want to talk about this a little bit. If you have a fixed value as a median, and you might have some uncertainty around it, but the value itself is independent of the quantity of damage, then you would just provide a single value, and you get a model like this. If there's a few damaged components, or if there's a lot of damaged components, your losses will have the same distribution. This is how HASIS works. However, newer methods like FEMA P58 recognize that if you have more damage, you can take advantage of economies of scale, and the repairs per component will be cheaper. And this is described by a function that starts at some plateau, and after a threshold, it drops. The cost of repairs, or a time of repair, drops, and it drops until it reaches a lower plateau. It can drop in one step, or it can drop in multiple steps. This is why it's called multilinear. If you want to have something like this, you would need to provide the points of these functions for each damage state like this. This is a syntax on how to put that into the table. If I move to the next slide, you can see here, for example, under damage state 2, I have 4 numbers because I want to have a drop. I want to have a multilinear option with 2 points. That's what FEMA P58 does. Okay, you can have as many points as you like. So even if you want to have some fancy function, maybe an exponential drop or something like that, you can have a really good approximation using a multilinear. So there's no good reason, at least as far as I understand, to go beyond this in complexity. But if you need something even more elaborate, let us know, and then we can see what we can work out. Okay, so again, the idea is that it's the same schema for all methodologies. I showed you the more complex one first to see all the options, but now if you see how HASIS looks like, a lot of columns are dropped because HASIS has a deterministic consequence function. And you can see that for HASIS, if I'm looking at a cost, for example, cost consequence, it provides a loss ratio, and you can see the loss ratio for 5 different damage states, and that's it, because there's no uncertainty around that loss ratio in the basic HASIS approach for earthquakes in this example. Okay, we have the same JSON option for metadata. It's exactly the same idea that we had for fragilities. And then once you define your own ideas by changing the parameters or coming up with a completely new file, so having that CSV table, you can use the user-defined option in PBE to load it in, and then from that point on, you can use it in your analysis. Now, keep in mind that, for example, you can keep the FEMA P58 fragilities and only change the consequences if that's what you are interested in, right? And maybe you only change the consequences of a few functions. And then you load your user-defined table and then keep on doing the same calculation without having to worry about anything else. So this kind of ease of editing is, I think, an important feature in our tools. Okay, so we looked at what data sets are available and how you can change them. And I would like to finish by showing you two quick examples of benchmarking. So say you have some component available in FEMA P58 or HASs, and then you come up with your own. The first thing you might want to do is compare how your own component changes the results compared to the previous one that was already available. So we will look at first an example where we compare 3 different versions of a particular structural component, and then see how the losses for that particular component change as a function of demand. That's a relatively simple thing. And then the second example shows that you can put these 3 components in 3 different complex models, which look at the performance assessment of an entire structure. And only these components are different between those 3 models. And now you can look at the losses calculated for the entire structure using different components and see how changing that single component impacts the losses for the entire building. All of the files that I use for these examples will be shared with you. I'm not sure what the GSC folks use to make those available, but we will figure out something. So everybody who is here will have access to those files. And I am also going to share all of the slides with you. So you will be able to, and I encourage you to repeat these examples, and then you can use them as templates for your own studies. Okay, so I will exit from the presentation and then show you the examples next. I will walk through them rather quickly. You will not be able to follow everything right now, but my intention is that if you understand how it works, and if you have some experience with working with PBE, you will be able to repeat them by looking at the other webinars or the documentation. PBE is a rather complex tool that is difficult to explain in detail in half an hour, but I think you will be able to understand what we are doing. So I just started PBE. This is the default screen that comes up. And the way you can use these examples is that you just go to File and open one of the input files that I prepared for you. So you see I have example 1 and 2. These folders will be available to you, and there's an input JSON in that folder. So you open that input and everything is populated automatically. So I don't have to walk you through on how to what to set for each of these panels. You see that everything is set up. Now, the key here is loading your custom fragility database, right? So it's user defined. We are not using the FEMA P58 one. And if you look at the example, here we have this custom fragility DB CSV file. This is the one we load. And because we loaded this one, you can see that we have 3 components. These are the 3 components that we want to benchmark. If I open this file for you, just to show you how it looks like, the raw file that we loaded, I'm just pulling it from my other screen. This is how it looks like. So rather than having a massive table, now we only need 3 components. So we have these 3 IDs, right? And then these are controlled by peak interstory drift. These are 3 components from FEMA P58, but they are just illustrating what you can do with your own ideas, right? Imagine that you have 3 different components for a particular member or a non-structural element. And you can see how we have different parameters for limit state 1, limit state 2, and limit state 3 for the first 2. The third one doesn't even have a limit state 3, right? So it's a different number of limit states. It's not trivial to see how their behavior is going to be different under different demands. So what we do here is that we assign each component to this analysis. You see, these are the 3 components, and we only have one of them assigned to the building. It's not really a building. It's a virtual thing that we create where we will have a single component on the first floor, and we provide demands to excite that component, and we will compare the response component by component to those demands. The demands are provided here under demands. We choose from a file demands that we prescribed. I want to stop for a second to also show you this, because this is quite powerful. I provided two types of demands here. One of them is gradually increasing from 0.02 to 0.1. So this is scanning the entire drift domain that I'm interested in, and I will see how the component responds to different drifts. While the other one is based on some analysis that I did, and this is the actual drift values from 50-gram motions. So it's a more realistic distribution. And you could add as many as you like. So you can compare component behaviors under different demands with this approach. Okay, so once we are done with this, we can click run. And then here in the bottom, you see what's happening. And as soon as we move to the results pane, the calculation is done. So this took maybe 2 seconds. So of course, it was not too exciting. And these are global results. So if you run an actual structure, as we will see in the next example, then these results are more meaningful. Now we are running just a component test. So these results are not very helpful for us. We have to go and look at the raw data and process it. You can find the raw data by going to the preferences in PBE, and it shows you where your working directory is, your local jobs directory. This will be some folder on your computer. You can change it to anything that you like. And this is where your results will be stored. Now, let me show you how it looks like. So if I pull this in, this is the same folder. And you have all of these are the results of your analysis. You have component quantities, demands, a summary file, damages, and then decision variables. Everything about these is described in the documentation in detail. What I did is that as part of your package, I have a post-processing folder where I copied the results that I got. You should have the same results, but just in case it doesn't work, you can still see how those results look like. And I have a Jupyter notebook there to show you how to post-process them. Let me show you that notebook real quick. It's nothing fancy. I believe everybody has their own post-processing ideas and needs. So this is just to show you what you can do with such results. So we are in Jupyter Lab now. You can also post-process with Excel, MATLAB, or anything else. These are just tables, right? So in Jupyter Lab, I open the files, and then I load the demands that I've just shown you, and I load the damage information for each component from each type of demand. I get if it's in damage state 1, 2, 3, or 4. And then using this data and the loss data, I can create such plots. So here, and you can look at this Jupyter notebook, see what exactly I did, but in concept, I took the demands that go from 0 to 10% drift. And for each level, I have X number of results that I ran probabilistically with the calculation. And you can see, if I only show the first component, that this component starts to pick up losses and damages around 2% drift. And after that, it reaches a certain level around here at 4%. And after 4%, the losses are roughly the same, right? The distribution, you can see that. If I compare it with the second component, I don't see a big difference. So changing those parameters will not lead to a large difference. But if I compare it to the third one, which is much weaker, you can see here that there's a lot more losses at small drift levels. So even without doing a complicated calculation, you can immediately see the difference and where you can expect that difference. If the drifts are large, like 6%, the difference is not that big between the blue and the green dots, right? Now, this is a cloud. You might want to say, let's look at the median instead, or the mean of at each level. So I show you an example of how to do that too. And these are the mean values of those clouds. And again, you see the same picture, right? The blue and the red are roughly similar, and the green one is much higher losses at low drifts. Okay, so this is what you can get. And of course, you could look at damages, you could look at many more things, because you have the raw data of every realization in that set. I see that I'm running out of time, but I want to show you the second example too. So I will do it quickly. So the second example looks at a particular building. This is, I think it's a 4-story reinforced concrete frame. Let's go to the folder here. And we have 3 different models for that building using these 3 different options that we just looked at in the first example. So the 3 different kinds of concrete beam column connections are used, and we see how the results are changing as we change the beam column connection. So we can use the input file that is in the folder to open the settings. You can see that this is a much more involved calculation. There's again a custom database that you can load in that folder. Again, this is a database that includes all of the components that might influence that building. And you can see that now we have a lot of components, and we use these 3 models to describe the 3 different options. So model 1 uses the first option for our beam column connection, model 2 the second one, and so on. You can see here that if you focus on these 1041, 00, right? 1, 2, 3. If I load the second model, it uses the 021, 022, 023. And the third model will use the 070, 172, 73. So that's the only difference between these models. Again, let me point out how convenient this is. You don't have to worry about all of the other settings here for demands, for the damage calculation, including irreparable damage and collapses and all that stuff. The only thing you need to worry about is loading the right performance model out of these 3. And then you can do the same, click run, get the results in that folder, and copy it to the post-processing folder here. So in the second example, in the post-processing folder, we have 3 options for the 3 models. And what I show you, and this is the last step in the Jupyter notebook that is in that folder, is how you to load those results for the 3 different models, and then compare the loss curves. And you can see that if you look at the big picture, this building is mostly experiencing losses because of collapse and irreparable damage. So those column choices are only important for about 30% of the cases. Everything else is going to be controlled by other things. And for those 30% of cases, you can see that the green case, the weakest column, has a significant increase in the losses, right? That the losses are in the horizontal axis. But the blue and red cases are quite similar. Now, the blue is a special moment frame. The red is an intermediate moment frame. So it shows that even if you only have an intermediate moment frame, it's not going to make a big difference for this particular case. Okay, let me wrap up with this slide. Just suggesting you to look at other resources we have. There's a URL here. At this website, you have all of these things, links to documentation, links to our upcoming events. You can reach our forum and ask questions. And we have positions for visiting researchers that could be graduate students like you, coming to us, to UC Berkeley, and work with us on extending our tools if you are interested in that. And we also have REU positions. So if you know undergrads who you think would be interested, let them know and encourage them to apply. And I apologize for being a bit longer than I anticipated. I don't know if we have questions. Maybe if we have time for questions, I'm happy to stay. But this was what I planned for the talk part. Thank you.
Thank you, Adam, for that excellent presentation. I know, yeah, we're approaching 12 o'clock, but if people would still like to stay and ask any questions, now is the time. I would like to invite the audience members to ask any question they might have by either unmuting or typing that in the chat box.
I'd like to ask just one question. The structural dynamic results used in the PBE, does the structural analysis process itself happens within the PBE or outside?
You can do either. Let me show you. So inside PBE, you still see my screen, right?
Yes.
Okay, so inside PBE, we've been focusing on the DL panel. The DL is the damage and loss. Think about those puzzle pieces that I showed at the beginning of the presentation.
Yeah.
So there are others here before that. We focused on the DL because I was loading demands from a file. If you have some external calculation in another tool, and you only want to use PBE for the damage and loss part, you would do this. If you want to run the analysis within PBE, including the option to run on design state, because maybe you have some expensive calculation and you want to run hundreds of ground motions, for example, you choose from workflow here. And that means that I expect you to come here, choose a simulation option. We have different ones. If you look at EEUQ, another tool that we have, and all of the webinars that we have about EEUQ, those explain the options you have for structural response estimation. You can use OpenSeas models. You can use these two different options to automatically create models for different kinds of buildings, steel buildings or concrete buildings. And we have the MDOF Lu option, which is a stick model essentially for representing buildings in a very efficient but idealized way. So you choose that. You can choose your events. We have different models available for ground motions. So you could load records from peer NGA. You could do a stochastic ground motion generation. You can do site response analysis with soil columns and propagate ground motions that you provide through a predefined soil column. There's many things you can do here, including adding random variables at this step. So you could have a structural model that you have uncertainty about certain parameters of that model. You can specify the distribution functions for those parameters and then generate response quantities that are later used in the damage and loss part. So this is all available. It's just a bit more complicated than what fit into this workshop today.
Yes.
Hi, Doctor. I have a question actually. Sorry for maybe this is a naive question because I'm really new on this topic, the PV performance-based engineering application. But I want to really, it seems very interesting over here. So my question is actually when I do the analysis over here for a performance-based analysis on a structure, can I incorporate the time history data of a specific location in this software? The
time history of a ground motion or of a wind event?
Yes, it's a ground motion.
Yes. So under events, you can choose multiple peer, for example, and add specific time histories from files that follow the peer format. Or if you don't have them in the peer format, you can use multiple SimCenter. We have our own JSON format that you can read about in the documentation, and then have these files loaded here. If you have a lot of ground motions, you might not want to do them one by one, so you can load an entire directory.
Oh,
just like that.
Great. Okay, thank you.
Yes. Amir has a comment in the chat. Maybe I will read it because I think we are still recording, right? So for the sake of the recording, I think it's better to say this. So he says, I don't think hazardous fragility functions can be treated the same as P58. They are sensitive to intensity measure, not EDP, because they are system level fragility functions, not component level. It would be great if you can help me with this. Yes, I agree. They are not the same as P58 functions, but the structure of storing them can be still the same. They are driven by EDPs. They are controlled by EDPs, not they are controlled by IMs, so intensity measures, not EDPs, engineering demand parameters, but that doesn't change the structure of the calculation. It changes the demand that you feed into them. And that's what I showed with this slide. If you go to HAZUS here, when we are looking at the hazardous earthquake option, it's hard to see, but here it says peak roof drift ratio, for example. These are based on the capacity curves that are in hazardous. So this is peak roof drift and not peak interstory drift, because it's a building level EDP. So you can recognize these differences by changing the demand type that controls the fragility function, but the calculation itself is still the same. You provide a distribution of demands and you will get a distribution of damage states. That does not change between FEMA P58 and hazardous, in my opinion. But Amir, if you have other thoughts, I'm happy to talk about it even now or later.
That's great. Maybe we'll have, yeah, I think it's time to wrap up the Q&A session. If anybody else have any other questions, please feel free to reach out to Dr. Adam Zarnozay, and we'll share this recording also on the YouTube channel, and it'll buddy. So with that, I'll just want to share my screen and for some closing remarks. So I would like to, first of all, thank everybody who attended the workshop today, but most importantly, a huge thank you to Dr. Adam Zarnozay for making time for us and delivering an excellent presentation. Also, thank you to my co-organizers for their efforts in making this a successful workshop series so far. And I would also like to thank Robin Nelson for her continual support and guidance, which has been instrumental in the success of the events NHERI GSC has put together so far. I would like everybody to, I'd like to invite everybody to join us next month for part 4 of the Research Tool Workshop series. It's going to be about simulation of regional hurricane impact using SimCenter tools, presented by Dr. Stephen Gavrilovich. It's going to be on February 10th, Friday, 11 a.m. Central Time. Once again, here are the QR codes and links to get involved with the NHERI GSC community and join the working groups of your interest. Give a second for anybody who's interested to scan these QR codes. Finally, I would like to mention 2 exciting opportunities we have been working on for the NHERI GSC members. We welcome you to participate in the inaugural NHERI GSC mini conference and collaborative research challenge by scanning the QR codes or by following the links provided on the slide. You can participate in one or both of these events. The mini conference will be a fully virtual event on May 26, 2023, where NHERI GSC members can present ongoing research such as posters, papers, research panels, professionalization, and other workshops on natural hazards related topic across all disciplines. And the collaborative research challenge is designed to facilitate interdisciplinary research that can be presented in academic or professional setting and or published in academic or technical journals. The groups will be assigned by organizing committee and who will work together for the next few months and present their preliminary findings on the day of the mini conference on May 26, 2023. More information will be provided by the NHERI GSC leadership through social media posts later today. So stay tuned for that. Thank you everyone once again. And thank you once again, Adam, and everybody have a great weekend.